Hi students, today we will discuss about solenoid. This is one of the beautiful arrangement of a wire. Let's say you are aware about that length. Let's say I have one length, naming it as a L, and I am just wounded it out in a number of helix or turns. It will look like a spiral or look like a spring. So it might contain some of the length, but ideally speaking, practically that whenever your length has been converted into a number of loops, it might be something different. So you can say that a solenoid is having such type of a spiral shape, but whenever it is opened, so it's higher than its actual comparison with the normal length. So spiral part is there, so I'm just drawing such type of a spiral part to give that idea to you. Basically such type of a number of turns are very much closely packed, so I have just shown such type of arrangement in front of you. These are, let's say, points. I am just noting as a dot notations, and I am putting such type of points as a cross notations. You are aware about dot and cross notations. Whenever your magnetic field lines are coming outside, we are putting dot notations, and whenever magnetic field lines are going inside, we are putting that across notations. Let's say this is my direction of current, so I'm applying my thumb rule. So as per my thumb rule, my pen and my thumb's direction is giving me the direction of current, and this is called as magnetic field lines. As you can see that magnetic field lines are just again passing from outside to inside. So this is the primary arrangement of it. You can see also such type of points where P is called as a magnetic field at the central part and Q is magnetic field outside. So you can observe that at point Q, magnetic field is somehow in a diminished nature or lower in nature, but at a point P it would be quite stronger. So you are aware about that Ampere circuital law. I have told you that the magnetic field can either be in the direction of your current, might be perpendicular or might be zero. So you can observe that your magnetic field at this point would be inside, so it would be a stronger part, but whenever it is outside, it is gradually decreasing. And this is very much nearer. Such a type of wires are very much closely bounded, so both are nullifying effect of each other. So on the surface we cannot find it about magnetic field because of the uniform magnetic field is equally distributed all over the arrangement. So I'm using such type of a notation. B dot dl is equals to mu 0 into I, and you are aware that theta must be 0, so I can have a B into L because integration dl is called as L into mu 0 I. So I can have a magnetic formula, magnetic fields formula is called as B equals to mu 0 I into L. So it is giving us a sum of the idea of a previous clip, as I have told you that magnetic field is gradually decreasing, but in solenoid internal part where at the center its magnetic field is a stronger one. Let's say I have shown you such type of a U-shaped coil, and in the U-shaped coil I have placed one conductor which is having the square loop, and that is called as the area of H and H. So let's say this is my direction of current. I want to find it out magnetic field for such type of loop. I have, you can see that I have placed that such type of a dot notation. It means that my magnetic field lines are going outside, and here you can see that there are cross notations, so magnetic field lines are going inside. So both are fulfilling the conditions of Ampere circuital law. So first of all I am just putting a closed loop, and I have my area A, B, C and D. Integration of B dot dl is equals to mu 0 I. So right now I want to just calculate it. So first of all I am just saying that my current is passing from A segment to B segment, and I'm just putting that first of all B dl cos 0 plus integration from B to C and B dl cos, that is why from B to C it is called as a cos pi by 2, integration from C to D, it is also having B dl, and then I'm putting that cos pi plus integration of, let's say, starting from D to A, and that is again B dl, and cos pi by 2 is equals to mu naught I. As you can see that my direction of current from A to B is in the direction of my current actually passing, so my angle would be 0. You can see that B and C both are perpendicular to this current carrying loop, so both are pi by 2 pi by 2. Here there is a current which is in opposite direction, that is why I have placed that theta equals to 180 or pi. but frankly speaking it is outside of a magnetic field or current carrying conductor area, so it would be 0. So its angle having no impression, so this would be making that my magnetic field 0. Here my angle will be pi by 2, that is also making an angle of a 0, and again my pi by 2 would be there, so my magnetic field will be 0. So you can see that to fulfill such type of condition or arrangement, we must follow Ampere circuit law. Our current must be there and it must be placed into the region of a magnetic field line. If it is above or beyond that field line, then magnetic field will be 0. So only B2C, C2D and D2A is of no use. So I can have that integration of A to B and BDL is equals to mu naught I is available to us. I am putting that B is outside of integration, A to B area, and DL part is called as a mu 0 I. You are aware that you can see that its length is h, so B minus A or integration DL. So I am just mentioning that L equals to AB part is called as h. So my equation will give me BH is equals to mu 0 I. So you can see that it is the same equation which we have just previously discussed. Instead of right now we have placed h, we had placed that L over here, but if you have just taken only n number of loops, so your equation will be just 4 n loops. For n number of loop, your equation will be something different. It is called as a mu 0 n number of a time of a current divided by h, that is called as our equation of magnetic field. You can observe that if instead of such type of I have just placed some distance between them, but if such type of current carrying conductors or wires which are specifically wound in a circular or spiral form, if they are very much close, then magnetic field at the central part, its midpoint part, is very much stronger, because that number of current carrying conductors and loops are more. That is why at the central part magnetic field is uniform and very much stronger, while on the surface and outside will be gradually weaker, because of that magnetic field is beyond some distance, it is having inverse proportional nature. So for that we will just use such type of formula, n divide by 2 pi r, or in future we will just use n by l, because sometimes number of loops per length would be something different. So we will just say that that is called as a number of turns or loops per length, or number of loops per circular radius. So we will use that part small n. So keep in mind whenever we will solve such type of examples of a solenoid or toroid, if they have mentioned that only number, it means that only n is there. But if they have mentioned unit length and number, that would be n by l, and if l is unit, so it would be only merely n. But if number of turns per radius and number of turns per length is something different mentioned to you, so be careful. They are discussing about small n, so first of all you have to talk about capital N, and you have to just calculate the 2 pi r or radius, or capital N number of turns and length. Then and then you are discussing about solenoid properly, otherwise you might be missing some data. So in the next clip we will discuss about toroid, and in a toroid you can say that it is having the same type of nature, but it's a geometrical shape, and it's some of the properties are different from the solenoid. So after learning the toroid, you will be capable enough to compare solenoid and toroid. Thank you.